Hello and welcome back here to Spherical Chicken in a Vacuum. Today we are talking about polymers. You will notice that the format of today's lesson will be a little different from usual. I decided to reduce the time so that we can talk on different topics and the videos can stay below 10 minutes of length, okay? And there are three main things I want to speak to you about today. And one is the definition of polymer. The second one is the difference between plastic and polymer, because there seems to be a lot of confusion about this point. I don't know why. And the third point is to introduce you to the main mechanism of polymerization. And let's start from the definition. Polymer. It's from Greek polis, which means many, and meros, which means parts or units. So if we imagine like a train and we take just one wagon and we multiply the wagon, we can obtain a train, and it doesn't really matter if the first wagon is different from the others, like in this picture, the blue one, or if we alternate, for example, green and red wagons, this is still a polymer by definition. Okay, so it's a macro molecule made of single units. And the word polymer is not so old in the end, because it was created by this guy, John Jacob Berzelius, which was a Swedish chemist, and he used polymer for defining compounds that have the same elemental composition but different molecular weights. Sounds difficult, but it's not. Let's take an example like this: acetylene, two carbons, two hydrogens; benzene, six carbons and six hydrogens. These are polymers of each other according to Berzelius, because benzene has three times as much carbon and three times as much hydrogen than acetylene. So these two are polymers of each other because there is a same ratio, one carbon for one hydrogen, but benzene has three times more than acetylene. The modern definition of polymer was created by this other guy, which is Hermann Staudinger, and he's a German chemist, and he used polymer for macromolecules that are composed of long chains of repeating monomers, which are covalently bonded together. So he won the Nobel Prize for this, and the most common example of polymer is probably this polyethylene. But other polymers are, for example, DNA or even proteins, of course, because polyethylene is made by repeating the same unit, which is composed of two carbons and four hydrogens, that you can see in the picture, over and over. DNA has four different units, and they are connected together, so it's a little bit more complicated, but still it's a repeating of units. And proteins are even more complicated because they have substructures that are made of single elements, so it's much more complicated. But in the end, they're chains of units repeated over and over and over again. Not in the same sequence, maybe, probably, definitely not in the same sequence, but the building blocks are the same and they're repeating along the chain. And let's go to the differences between polymer and plastic. So polymer by definition, as we saw, is any macromolecule which is composed of long chains of repeating monomer units covalently bonded together. But plastic, on the other hand, are only synthetic materials that are made of polymers, but that can be molded into shape while soft. For example, because we rise the temperature and they soften, or because they are in a liquid or viscous state, and then we make them hard somehow. Okay, so this means technically that all plastics are polymers, but not all polymers are plastic. And I think this is very easy to understand if we think about DNA. DNA is a polymer, as we saw, but for sure it's not a plastic. I don't think any of you would call DNA a plastic material. And yes, DNA is a material. And let's go to the mechanism of polymerization. And we start with my favorite, which is polyaddition. Okay, it's very simple. And to make it even more simple, I will use teddy bears as an example. Let's take this cute teddy bear. Let's paint his arms one blue and one red, and let's establish a rule that the blue arm can only touch the red arm. So if we want to make a chain of bears, we just need to open the arms of the bear and connect the blue with the red of another teddy bear. And in this way, we make a teddy bear polymer, okay? And we can also change the teddy bears with other animals, like this dog, and it doesn't really change. I mean, this is still a polyaddition, and it doesn't produce any byproduct. So the two teddy bears can connect to each other without releasing any chemical. And an example is the one I showed you before of the ethylene that becomes polyethylene. And if we take the basic molecule and we see that there's a double bond, if we break just one of these two bonds and we open like the arms of the teddy bear, we can connect then other units, and you see that we don't need to get rid of any atom. That's why we don't have any byproduct. In the case of the polycondensation, the molecules are usually a little bit more complicated. In this case, for example, the teddy bear is holding one lock bear. One lock in one hand and one key in the other hand. So we cannot connect the teddy bears with each other like this, right? So what we do is that we get rid of the lock and key to connect the teddy bears together. So the teddy bears are connected together, but we release a byproduct, which is the lock with the key. For example, if one arm of the teddy bear has a OH and the other arm has a H, that H can connect to the OH of the next teddy bear and form a water molecule that is released as a byproduct. Okay? And example of these are a little bit more complicated, as I said. This is, for example, lactic acid, and if we get rid of one OH and one H, we can connect it to another lactic acid, forming this polylactic acid, which is the material which constitutes the filaments of your home 3D printers, for example, polylactic acid, PLA. And there is one last type of polymerization that I want to talk to you about, which is ring opening. But in this case, I cannot use the teddy bear, as I need to use a snake. And unluckily, I'm not as good as drawing snakes as I am with the teddy bears. I'm sorry. But it's very easy to guess how it works, because I painted the head and the tail of the snake in blue and red, like the hands of the teddy bear. You need to do is open your snake and connect your snake with another snake, head to tail. This is what happens in ring opening polymerization. You have one ring somewhere in your molecule, you open it, and those open rings can connect to each other. One example of this is the formation of PGA, polyglycolic acid, which basically starts as a ring-shaped molecule like that, and we open it and we can connect these units together, forming PGA, polyglycolic acid. And this is everything for today. We defined what polymer is. So it's a macromolecule made of units repeated over and over that are connected in covalent bond. We say that we explain the difference between a polymer, which is of units, and plastic. Plastic materials are only the synthetic made polymers that can be softened to molded. We molded when softened, actually. And we explain the three most common, most famous, most fun to show, to see types of polymerization. And this is everything for today. Thanks for listening, and see you on the next lesson. Bye.